one p-type substrate, one n-type substrate, and there will be a junction between these two p and n layer. But whenever you want to
माझे
use
बुक
this
एक
particular
मिनिट थांब
diode
घ्या
for the
ॲक्च्युली
power
दुसरा
applications,
करून
so
5
you
घ्या
have
बरं
to
हे आमच्या
insert
आत्ता
an
जरा माझं
extra drift
एक्स्ट्रा
region,
सुरू आहे म्हणजे माझ्या
right?
विषयाचं
That drift region
तास
allows
दीड
you
तास
to
चालेल
enhance the voltage handling capability. So the size, or you
11:30
can say
मिनिटं
that the
झाली
length of the drift region will always decide that how the power handling capability will be there for particular
चालेल
device.
हो
And if you want to increase the current rating, so that means you just need to increase the cross sectional area. So whenever you are like increasing the cross sectional area of a particular device, let us say PN device, so then you can say that the current handling capability of that particular device can be increased. You can think like that. This is a normal PN junction diode, P and N. And when you want to utilize this for the power electronics, you just need to insert one extra layer. And that extra layer is basically known as the drift region. So this drift region will decide the power handling capability of that particular device. So in power electronics, you will find that each and every device is associated with the power applications only. That is why the name coined like power electronics. And in signal electronics, the applications are like related with the low power applications only. And these devices, the signal devices, you can say that handles very low power applications at very high switching frequency compared to the power devices. So in signal electronics, the power level will be like lower and the frequency level will be higher. You can take an example of the signal electronics like signal diode, Zener diode, LEDs, Vector diode, etc. But same thing will be like applicable when you increase the power rating. They all are like come under the category of the power electronic devices. In fabrication of like, you have to like think this way that in fabrication of the semiconductor devices, when we improve one quality, the other quality may be affected, right? That means we cannot improve all the qualities in a single device. Likewise, you can say that if you want to increase the power rating, so definitely there will be a compromise on the frequency, right? And on the other side, if you want to increase the frequency, then definitely there will be a compromise on the power rating. I think if you have gone through the power electronic devices, so you just need to classify like initially, I think you have gone through power diode, then SCR, then GTO, then power BJT, then MOSFET, and then IGBT. Now, if you compare all these devices, you will find that MOSFET has the highest frequency handling capability. You can say that you can operate the MOSFET at a very high frequency, right? But on the same side, the power handling capability of the MOSFET or power MOSFET, specifically, I am talking about the power MOSFET only, because now onwards, if I am talking about MOSFET, it means it is power MOSFET. If I am talking about IGBT, it is power IGBT. So when you compare all these power electronic devices, so you will find that the MOSFET has the highest switching frequency, but the power handling capability will be lower. On the other hand, the SCR has the highest power handling capability, but the frequency will be like on the lower side. So there will be like a continuous, you can say that one quality will be like increased, other quality will be like decreased, right? And you all know that in power electronics, all the devices are usually used as a switch, or you can say that all the times they will be like utilized as a switch, right? So we can utilize the switch in 4 different modes, and it is not like necessary that all the devices will be like supported each and every mode. Some devices may support 2 modes only, some devices may support 3 modes, some devices may support 4 mode, right? You can take an example of like SCR, right? So SCR is like what? It is like supporting 3 modes. If you are having an idea of all the 4 modes, that means the SCR is particularly supporting the forward blocking mode, because up to a certain level, this SCR forward breakdown region will not break. After that particular voltage, you can say that this breakdown occurs and the device will be like in forward conduction. And there will be another mode for this particular SCR is like reverse blocking. So your SCR is like working in 3 modes. You can take an example of simple diode, power diode. So in case of the power diode or the simple diode, you can say that the diode will be like working only in 2 modes, that is forward conduction. Immediately when you apply the voltage, anode will be like positive, cathode will be like negative. So immediately your device will be turned on, right? Then there will be a forward conduction. And you can also think that whenever you apply the reverse voltage, so there will be a reverse blocking capability, and that will be like, you can say that that mode will be there for that diode. But in SCR is basically a semi-control device, right? So in because of this semi-control nature, you can say that you can control the device. That is why there will be a forward blocking mode, and then forward conduction, and then reverse blocking. So similarly, you can go for other devices also. Like you can take an example of triac. And triac, the beauty of the triac is like that This is like the only device, or you can say that one of the very few devices that can be utilized in all the four modes. Correct? This triac is treated as an AC switch generally, right? Because it supports all the four modes. So you can say that it can be used in AC voltage controller. This is the application of the triac. You can use this for the AC voltage controller or fan regulators, you can say that. So based on the mode, based on the application, or based on the power and current handling capability, different power electronic devices will be utilized for different applications. Now you can take an example, like suppose if you are going for the application part, you can take an example of mobile charger. All of you are having mobile chargers, laptop chargers. So in the mobile charger, you just have to utilize one rectifier, because first of all, you just need to convert the AC that is coming from the, like your national grid. You just need to convert that into a DC. So AC to DC conversion will be taken care by the rectifier only, right? In power electronics, I think you have gone through four kind of the converters: AC to DC, that is rectifier; then DC to AC, that is inverter; then DC to DC, they are like known as the DC to DC converters and the choppers; and then AC to AC, that is voltage controllers, or you can say that the voltage regulators, right? So for 230 volt to the desirable level, because your battery require a certain amount of voltage level, so for that, and that voltage level should be like DC. So for that case, you just need to convert 230 volt AC into DC. Why I have taken this 110 volt and 60 hertz? Because if you want to talk about the universal charger or universal adapter, that means you have to like follow the convention that will be like applicable across the world. Suppose in USA, the supply range for the single phase system will be like 110 volt 60 hertz, right? So for that case, I have considered this. Now your rectifier is like converting the AC into DC, but that DC is like not pure DC. You can say that the output of the rectifier is pulsating in nature. Suppose you have like full single phase bridge rectifier. So in that case, the output will be like, let us say alpha is equal to 0, right? Alpha is like firing angle. So the output will be like 2 Vm by pi. Roughly you can say it is like around 0.9 of this VRMS. But the battery will require a lower voltage, right? The battery will require a lower voltage for charging, right? So you have to connect extra DC to DC converter, right? That DC to DC converter will try to regulate the DC, right? Try to regulate the DC and provide the certain level, that level required by the battery, right? Suppose your battery is like 5 volt battery, so that has like specification at 5.5 and 5.7 voltage will be there. That means the battery is fully charged. And if voltage is like 4.2 volt, that means the battery is fully discharged. So in between these ranges, the voltage across the battery will be there, and accordingly current will be like drawn by the battery. So you will find that there are two stages that will be utilized to charge the battery, and all these two stages are the power electronic stages. First stage is rectifier, then it is power electronic converter, that is DC to DC. Now what are the requirement of this? You can say that the power electronic stage. So first requirement is this DC to DC converter, or you can say that this power electronic circuit will provide the voltage and the current regulation, right? Voltage and current regulation means whether the voltage is like increasing from 230, or you can say that decreasing from 230 to 110, but the input side of the battery should be maintained at 5 volt or 5.5 volt, right? That voltage will be regulated by this DC to DC converter. So this is like beautiful application of this DC to DC converter. The voltage is regulated, right? And similarly, the current is also like regulated, correct? Another advantage is like isolation. Or you can say that another application or requirement of this power electronic devices is like to provide the isolation. Isolation is very important, because sometimes you have one power circuit and on the another side you have one control circuit, right? So control circuit, the rating of the equipment or rating of the devices on the control side will be like very low, and on the power side you are handling a very large power. So there will be like difference in the ratings. Another thing is that if there is any fault that is happening on the power circuit side, right, and if there is no isolation, so that fault and the high amount of the current can flow through the like control part. So that can damage the control circuit also. So my question is, and my like requirement is that we just need to provide an isolation between the power side and the control side. So therefore, this power electronic devices and the extra auxiliary circuits are required to provide the isolation. Isolation is very important to provide the separate ground for control side and power circuit side, right? So these are the two major requirements. You have to vary, you have to regulate voltage and current, and you have to provide the isolation by using the power electronic converters, right? So this way you can say that for maximum applications, you can say that Power electronic converters are essential, power electronic interfacing are required, and if you are having power electronic device, you need some knowledge of control, because ultimately you have to control the power electronic device. Whenever you want to operate any power electronic device, you have to provide a pulse, you have to provide a gate pulse, you have to provide a signal, right? So you have to require certain knowledge of the control so that you can control your closed loop, and then you can provide the gate pulse to that particular power converter. Another requirement is like you have some knowledge of sensors. So because whenever you want to operate the control, you need to sense some quantities, that is voltage, current, from the load side, from the distribution side, and accordingly your intelligent controller, or you can say that the control algorithm that you have provided inside the controller, that controller will decide the switching pulses, right? So this way you can say that the entire circuit will require a knowledge of control, a knowledge of circuit theory, a knowledge of sensing and like measuring equipments. This is like another example of this power electronic converter. Suppose you want to control the speed of the drive, or you want to control the induction motor that you have connected. So in that case, first you have to use this AC to DC rectifier, right? And rectifier will provide, like, initially on the AC side you have 50 hertz frequency, and you are going for the V by F control. Whenever you are going for the V by F control, that means you have to control this frequency and you have to vary the frequency. So for that case, first you have to convert AC into DC, and this AC into DC means you just need to utilize the rectifier. So you have utilized this rectifier, right? So here 50 hertz AC is there. Now converted this into DC, and then again inverter is required, and this inverter is basically converting this DC to AC with variable frequency, right? And then you can say that you can control the speed of the induction motor. So again, for this application, the application is like speed control of the induction motor, right? And you can say that you are supplying AC to the induction motor, then this power electronic medium is required to control the speed of the motor, correct? So this way you can take so many examples, and each and every example you need power electronic medium. Now another example, suppose you want to take that renewable energy sources, they are connected to the grid with the help of power electronic converters. Suppose you can take an example of solar photovoltaic system. So the solar photovoltaic system is like providing a DC, right? It is like a current source. Solar photovoltaic array if you are taking, or solar photovoltaic panel you are taking, so that means that is like a current source, right, giving the DC. So first you have to convert the DC into the usable form, and then you have to integrate to the existing grid, right? So again power electronic medium is required, and whenever you are like integrating, you just need to control. So control is also required in order to handle the power electronic devices. Similarly, you can take an example of battery charging, that is already taken in the last slide. You can take another example of wind energy conversion system. So in that case also you need back-to-back converters. So again power electronic equipment and power electronic converters are required. So my like thinking is that whenever you are going for applications related to the renewables, right, then you need power electronic medium. Essentially you need power electronic medium. So that is why in this entire lecture I just want to cover few of the basics of the power electronic converters, and then I will also provide the development and design of the few of the converters, and then how to control these converters for particular applications. So I will explain about this solar PV integration, how the solar PV is basically integrated to the existing grid, correct? Now suppose you have a knowledge of this power electronic devices and power electronic switches. So now please tell me, can you fire or can you drive a single switch with the help of a single pulse? Just the pulse is coming from controller. See, whenever you are getting a pulse from the controller, because you can take an example of IGBT or MOSFET. So IGBT and MOSFET both are like voltage control device, you all know. So if you are taking an example of IGBT and MOSFET, then you will find that you need a particular amplitude gate pulse, and that gate pulse will be like provided by the controller only, right? Because you have digital controller, right? These days digital controllers are very popular. DSP, digital signal processing, microcontroller, FPGA, DSPs, everywhere you will find different digital controllers. So the digital controllers are providing the pulse in the range of 0 to 3.3 volt or 0 to 5 volt. But your requirement is like 0 to 15 volt for the IGBT, or you can say that 0 to 12 volt for the MOSFET. Now take an example. In this example, I have taken like, this is your voltage source, this is your voltage source, and this voltage source is connected with this IGBT, and a load is connected. You can say that a lamp load is connected, right? Now my question is that can you provide the gate pulse directly from the controller to this gate point? Because controller is giving the pulse in the range of 0 to 3.3. This is your digital controller, right? So this pulse is like 0 to 3.3 or 0 to 5 volt max to max. But you cannot provide directly this pulse to this gate, because gate will require minus 5 to 15 or 0 to 15. You can say that this minus 5 is required to sweep out the excess charge carriers present in this inner layer of this IGBT, you can say. Now you have to develop extra auxiliary circuit, and that extra auxiliary circuit is nothing but your gate driver circuit. So you have to develop a gate driver circuit for a single IGBT. Now you can think of the inverter. In the inverter you will have 6 switches, so you need 6 gate driver circuits in order to fire, in order to drive all the switches in the inverter. And if you want to develop the driver circuit, so you need one optocoupler IC. So this is your optocoupler IC, TLP250. You can take any optocoupler IC. There are so many optocoupler ICs are available. Now the function of this optocoupler IC is that it will provide the optical isolation, right? Isolation means, I have already told you that the ground of this side, this is like control side, and this is like power side, right? So in the power side you will find that the ground is different. Here the ground is different because this TLP250 is providing the isolation, right? Because in TLP250 there will be optical isolation, right? So 2 diodes are basically, internally you will find that 2 diodes are utilized, and 1 diode is basically emitting the rays or intensity or light that will be like activating the other diode. So this way the configuration will be there, but the point is that this will provide the optical isolation. And the arrangement of this resistance on the input side and on the output side, right? I will explain in detail about this gate driver circuit, but here you will just need to understand that what is the requirement of this gate driver circuit. So on the input side some resistance is required, on the output side a resistance is required, and so that you will able to get the amplified output, that is minus 5 to 15 volt. This IC is like 8-pin IC, and this IC will require a DC supply. So in order to get the DC supply, first you have to generate or you have to develop the regulated DC supply. So this TLP250 will require plus 15 to minus 5 volt regulated DC supply. So first you have to develop the regulated DC supply, that is you are getting 230 volt 50 hertz from the AC mains. Then you have to use this step down transformer, right? This is like center tape step down transformer. So 232 15015, the transformer that you should use. After this you are getting here 15 volt 15 volt. Now you just need to utilize a bridge rectifier. You can take any bridge rectifier, you can take 4 diodes and you can create your own bridge rectifier. This is like uncontrolled bridge rectifier, right? So this bridge rectifier is like a series of VR rectifiers you will find in the market. So this bridge rectifier is utilized to convert this AC into DC. But the output of this bridge rectifier is like having some pulsating nature. Now output of this rectifier will be like this only. This will be the output. Now you have to convert this output into fixed DC. In order to get the fixed DC and in order to regulate the DC, you need linear regulated ICs. So 78XX and 79XX will be the linear regulated ICs, right? 78XX and 79XX. 78XX will be like utilized for positive side and 79XX will be utilized for the negative side. So 7815 means it will provide a voltage of 15 volt. So first you have to like utilize 2 capacitor. This capacitor range you can take 35 volt and 2200 microfarad. Similarly, this capacitor will be like in the range of 25 volt 1000 microfarad, right? And this regulated IC will be utilized to provide a constant or regulated output at output terminal. So similarly, this 7905 is utilized to provide to get the minus 5. This is not plus, this is minus 5, right? Because 79XX will provide the negative voltage. So this way you will have to generate this plus 15 to minus 5 volt, and this plus 15 to minus 5 volt will be given to this TLP250. This is like optocoupler IC, and according to this range of this voltage, that is minus 5 to plus 15, you will get an output. Suppose you need to develop a driver circuit for the MOSFET. So MOSFET will require, MOSFET you can take IRP 460. Right, this is one MOSFET. This MOSFET will require 0 to 12 volt pulse for the gate. Now you have to generate or you have to like develop a regulated DC supply of 0 to 12 volt. This 0 to 12 volt will be given to this TLP250, and accordingly you will get a output. The pulse output will be like 0 to 12 volt. That will be like given to this MOSFET or the IGBT that you have connected across this power network. Now when you provide this gate pulse, immediately your lamp will glow, and when you remove the gate pulse, immediately your lamp will like goes off. So this is like a controlling arrangement, or you can say that the control, this gate is having a control. Whenever you are providing the pulse, you are getting an output. Whenever you are removing the pulse, you are not getting any output. That means the driver or the gate driver that you have designed in the laboratory is like working perfectly fine. That means the pulse that are coming from this gate driver is like perfectly in the range. So when you provide the gate pulse, immediately the bulb will glow. That means the output will be there, conduction will be there, switching will be there, and immediately when you remove this, so the output will be like gone. So there will be no output when there will be no pulse. So this way you can think that this is the single IGBT or single switch. For this single switch, you have to use this much of the arrangement. Now you can think, suppose in case of the three-phase full inverter or three-phase inverter, three-phase two-level inverter is there, let us say. So in that case, you need 6 switches, or you need to fire those 6 switches. So this kind of arrangement will be like there for each and every switch. So handling of the power electronic equipment is like a big challenge. You have to develop certain auxiliary circuits so that you can handle the power electronic switches. Now, how this power electronic system will work? Suppose you have one power electronic converter. This is like one of the power electronic converter you have, and you have input on the input side. Either it is AC or DC, you can say that, or you can say that unregulated, right? Suppose it is a DC, you can say that this is like DC to DC converter. Suppose it is AC, you can say that this is like a rectifier. So this is like power electronic converter, right? And this power electronic converter is like connected to the load, right? So now the question is like that, the load requirement will be different, because whenever you are going for the power electronic applications, you have to understand about the characteristics of the load, because fully you have to read out the characteristics of the load. According to the characteristics, you have to design your control algorithm. This controller is nothing but, you can say that this is like digital controller. So in this controller, you will have a control algorithm, right? So this control algorithm will be like designed as per the characteristics of the load, because ultimately you have to control this thing, right? And in order to control the entire closed loop system, you need one sensor, right? Sensing arrangement. Suppose you want to sense the current, so you have to utilize the current sensors or the current transducer, you can say that. And if you want to like measure the voltage across the output, or you want to sense the voltage, so you need voltage sensing arrangement. So this output of these sensors will be like given to the controller, right? And in the controller, there will be a preset value, that is like reference value, right? And generally this reference value will be like compared with the estimated value. Estimated value means the value that you have estimated with the help of sensors, that is the voltage sensor and the current sensor, right? And then the error created, and that error will be like passed through certain controllers, like you can say a PI controller, proportional integral controller. And according to that controller will be tried to minimize the error, and according to that error, you just have to generate the switching pulses, and those pulses will be like given to the power electronic converter. So this will be like an entire closed loop. So in this case, semiconductor devices will be there, control will be there, conversion of the power will be there, right? So this power electronic is like a multidisciplinary kind of thing, right? You are like converting the power, you are using the control, you are using the measuring equipments or the measurement part, and you are like converting the power, electrical power, from one form to the another form. And because of these things, you can beautifully use these power electronic devices for so many applications. So this is like controller, and this power electronic converter is like the heart of this power electronic system, entire system, because ultimately you have to control this. And if you are able to control this in a good manner, in an intelligent manner, so your system will be like intelligent. Now come to the power electronic switches. So there are like two kind of the switches you will get, either uncontrolled, or you can say that the controlled. And one another you can say that category is also there, that is the partially controlled switch. So suppose you can say that thyristor is there. So thyristor is like partially controlled or the semi-controlled. That means you can control the turn-on process, right, with the help of the gate, but gate cannot control the turn-off process of the thyristor, right? Suppose you are giving gate pulse to the thyristor, that means the thyristor will be like switching on, right, turning on because of this gate pulse. And after that, if you remove the gate pulse, so thyristor will remain in the on state. If you want to turn off the thyristor, you just need to bring down the current that is flowing through anode to cathode below that holding level, right? Only in that case you can say that your thyristor will be like turned off. So in this case, this thyristor is like semi-controlled. Through gate, you can just only control the turn on process. You cannot control the turn off. Similarly, diode is there, so diode is like uncontrolled. Ultimately, whenever you are applying the voltage, immediately the diode will turn on. Now you can think of the fully controlled switches. So GTO is there, gate turn off thyristor. This is like pulse control. You have to provide the pulse at the gate terminal. Now you can also categorize like voltage control. So two important devices, power devices are there. That is IGBT and MOSFET. They are like most important devices for high power applications. And these devices are like voltage control devices. Voltage control devices because on the input side or at the gate side you will have one SiO2 layer, right? And there is no direct connection between the gate terminal and the inner N channel layer. If you are having some idea about the construction of this power MOSFET and the power IGBT, so there will be SiO2 layer. So because of that, you will find that you have to provide a voltage of certain magnitude so that the positive charges will be created below the gate, so that there will be a channel formation. So because of this, you will find that the IGBT and MOSFET are like voltage control devices, right? And this BJT is a current control device. So you will have different switches, different characteristics, and according to your application, you can use these devices. Throughout the, you can say that the course, throughout the application part, you just need to utilize these devices only. Now, your first device, whenever you are like going through the course of this power electronics during your curriculum, so you will find that first you have to understand about this devices, SCR, GTO, power IGBT, BJT, MOSFET, everything will be there. And then you have to go for this rectifiers. First is like rectifier. Rectifier is nothing but it will try to convert or it will convert the AC into DC, right? But when you carefully analyze the rectifier, you will find that this rectifier is like a problematic for the existing system. Why? See, this is like a Simulink diagram. You can also create this. You can also design a rectifier in the MATLAB, right? And you can connect a load across this rectifier and you can connect a suitable AC on the input side and you can measure the output side current and voltage and you can also measure the input side current and voltage, right? And you can take controlled or uncontrolled as per your requirement, right? But my question and my like observation is that whenever you want to analyze this rectifier, every time you have to analyze on both sides, right? On the AC side and on the DC side, because both side analysis is important. Whenever you are using this power electronic switch or because of the switching nature of the devices, there will be an effect on the source side, on the source current, right? Because of the switching arrangement, this rectifier will try to disturb the source side current, right? And this can be like carefully observed by the analysis on the AC side and on the DC side. If you are like having a good knowledge of the harmonic analysis on AC side and DC side, then you will be able to get the knowledge of this input side distortion. This rectifier is basically a useful device, no doubt. It will be like utilized in so many applications, a very useful device, but this rectifier will always try to inject the harmonic into the system, right? Because this rectifier will try to extract the non-sinusoidal current from the supply, and because of that nature, you will find that the harmonic will be like increasing on the AC side. So for this, I just want to know the behavior of this rectifier. This is single phase controlled rectifier, bridge rectifier. You can say that 4 switches are there, and these 4 switches are controlled through the pulses. So you can provide the pulse in the MATLAB. So pulse will be like provided to the rectifier to the switches. Input is connected AC side. This is your output. RL load will be there, and you can measure the input current, input voltage, output current, output voltage, everything you can measure. Right now, carefully observe the waveform. These are the related waveform of the rectifier that you have developed in the MATLAB and the Simulink. So you will find that this is the supply voltage, perfectly sinusoidal. Supply voltage is perfectly sinusoidal. This is the output current, right? Output current is like pulsating in nature. Now this is the voltage across the switch. Okay, this is the load current. Current is like getting near to DC because you have already considered the highly inductive load. Generally, whenever you are going for this rectifier and you have like high inductance, so you will have load current like almost constant, right? Because when you analyze the rectifiers and everything in the theory part, so every time you have to assume that okay, load is highly inductive. So when the load is highly inductive, load current will be like constant only. Now the important observation is that carefully observe this supply current, right? This supply current is like near to the square wave, right? Almost you are getting a square wave because of this rectifier. So this rectifier is trying to extract this kind of the current from the supply mains. That means the harmonic content will be like injected by this rectifier into the system, right? You can carefully analyze the FFT analysis because in MATLAB you have one tool, FFT tool. So when you analyze the FFT of this waveform, you will find THD of this waveform, right? Because THD is the total harmonic distortion, right? Have you some idea about the THD and about the, you can say that the form factor, everything? Because when you analyze the waveform, so there is like, you can say that harmonic analysis on both sides, on the DC side and on the AC side, right? So if you want to analyze the DC, so you have to define the form factor, or you can say that the voltage ripple factor. Whenever this voltage ripple factor will be like equal to what? 0. So there will be like no ripple, and at that time form factor becomes equal to 1. So when this form factor will be 1, voltage ripple factor will be 0, then there will be no harmonics on the DC side, right? This is the significance of the form factor. Similarly, if you want to go for the harmonic analysis on the AC side, you will find that distortion factor G and the TSD. These are the two important things. TSD is nothing but it is a measure of the harmonics on the AC side of the converter, right? So when this TSD will be like 0, that means that pure sinusoidal nature waveform will be there. So that is pure AC quantity will be there. No harmonics will be there. When this TSD is 0, you will get G value equal to 1. For pure AC, you will get G value equal to 1. So with harmonics, G always less than 1. Without harmonics, G value will be equal to 1, right? And G is nothing but the distortion factor, always measured in the power electronics, right? If you have carefully analyzed the harmonic analysis for the inverter, for the converter on the AC side and on the DC side, so these two things will be like defined. So now you just need to observe the THD of this supply current. So this is the frequency spectrum, you can say that, of the supply current, and you can measure this and you can analyze this by a tool in the MATLAB, that is FFT tool. So this is your source current waveform, right? Because of the rectifier, and see the TSD. The TSD is around 42.75%, right? And if you are going for the standard wise, so for IEEE standard, right, IEEE 1547 or 519 standard, you will find that the acceptable limit for the THD for the voltage and the current will be like 5%, right? And you are getting this much of the THD. So this is not acceptable limit, right? So whenever you are using the power electronic devices, specifically the rectifiers, see the effect. This rectifier is trying to inject the harmonics into the system. And now you have to use this rectifier, because this rectifier is a beautiful device. So many applications are there, but at the same time, you have to control the harmonics. So you have to control this rectifier and you have to control this power electronic device. So my observation is like that whenever you are using the power electronic devices, you have to control those devices in such a manner that you can also improve the power quality. You can say that you are able to reduce the harmonics in the system, right? Because ultimately, if you are like leaving this rectifier alone and this rectifier will try to inject the harmonic into the system, that is not a good sign for the existing system. So you have to remove those harmonics, or you have to control those harmonics. Similarly, I just want to observe the current spectrum of each and every rectifier that you have gone through your theory courses, right? That is single phase, half wave, single phase, full wave, semi-control, full control, 6 pulse, 3 pulse, everything, right? So let us have a look of the source current waveform for the different rectifiers. Like you have single phase uncontrolled rectifier, right? Uncontrolled rectifier. So typical current waveform will be like this much only. This is the waveform. And in this case, see the TSD. TSD will be like around 80%. And you will have high amount of the third harmonic component will be there, right? Now single phase semi-controlled bridge rectifier is there. In that case, this is the current waveform. So in this case, second, third and fourth, all the harmonic components are there, right? Now it is also essential to have a careful analysis of the harmonics, because when you know about the harmonics, you know about the behavior of the harmonics, right? You can design and develop a certain control so that your inverter or the converter that you are using, that converter will be trying to inject the same harmonics but opposite to the harmonics that is available in the supply system, so that they become cancel out each other, right? This is like nothing but a principle of the Saint active power filter that you are using, right? Saint active power filter will be like utilized, or you can say that the principle of the custom power devices. So in the custom power devices, these devices are generally utilized at the distribution end in order to mitigate the harmonics, in order to mitigate the or suppress the reactive current requirement, right? In order to improve the power factor. So in order to balance the current, in order to balance the voltage. So custom devices will be utilized at that place, or you can say that the FET devices. So these devices will be like, the principle will be like that. They are like having power electronic converter, and that power electronic converter will try to inject a current or inject a harmonic current. That harmonic current will be like opposite to the phase of the current that is flowing into the supply, so that the harmonics will be like cancel out and there will be like a smooth sinusoidal signal on the AC side. So see the effect of this rectifier, single phase semi-controlled rectifier bridge. These are the harmonic. If you are having 6 pulse converter, right? 6 pulse converter means 3-phase full wave rectifier. 3-phase half wave rectifier is like 3 pulse converter. You have some idea about the 3 pulse converter and the 6 pulse converter. See, in 3 pulse converter, the output will have 3 pulses. For 0 to 2 pi period, you will have 3 pulses in the output in the DC. And when you are going for the 6 pulse, you will have 6 pulses output for 0 to 2 pi period. So see the THD. And this 6 pulse rectifier is like without filtering arrangement and without input reactor. Nothing is there. Directly 6 pulse converter is there. See the THD. The current waveform will be like completely distorted. Right? There is no use of this kind of the waveform. This waveform is like completely equipped with the harmonics. See the TSD. TSD is like 80%. This is a use. You have to maintain the TSD below 5%, but actually it is like 80%. So this gap is very large gap is there. And see the harmonic content, 5th, 7th, 11th, all the odd harmonics will be there. Next, you can observe this 6 pulse rectifier output voltage filtering with 3%. You can say that the reactor filter or with continuous output current will be there. So in that case, the output waveform will be like, or you can say that the current waveform will be like little bit improved. That is why the TSD will come around the 40%, right? But still the TSD in the higher side, right? And whenever you are using this 6 pulse converter with large inductor, still in that case you will find that 28% TSD is also there, right? Suppose you have highly inductive load, you have considered that. That means you are getting constant output current, but still the current that the rectifier is extracting from the supply is like this kind of the nature. So the TSD will be like 28%. So this is also like not acceptable, because acceptable limit is like 5%, right? And when you go for the another like 12 pulse rectifier, right, then only you can say that the TSD will be like 15%, right? But the application of these kind of the rectifiers is like not so much applications will be there. You have to use the 6 pulse rectifier, or you can say that the 3 pulse rectifier, or single phase full wave rectifier, half wave rectifier. For those cases, the TSD will be higher, and you have to remove or you have to reduce this TSD. You have to mitigate the harmonics, right? So before going to that part, you just need to have a clear idea about the harmonics, right? The which converter is like responsible for which kind of the harmonics. Then you can develop a suitable control for the particular harmonics. So let us say this is like general observation. All of you have some idea about this observation, because you have gone through the signal system, and you will find that whenever there is a symmetry, when both positive and negative half cycle of the waveform have identical shapes, then you can say that only odd harmonics will be there. And when there is no symmetry, you can say that then even harmonics will be there, right? So this way you can classify, and you can observe that when the waveform is there in front of you, so immediately you can say that, oh, this waveform is like symmetrical in nature. So you can say, you can comment that this is like 3-phase system. So there will be like 5th harmonic, 7th harmonic like this. And if the system is balanced, so there will be no triplen harmonic. And if the system is unbalanced, so triplen will be there, odd will be there. So this way you can classify the harmonics. And triplen harmonics, source of the harmonics, everything will be there. You can go through the harmonics, right? I'm not going in detail of this harmonic portion, right? Because you have like clear idea about the signal and system. You can classify the harmonics, and according to the requirement, you can design a converter, or you can design a particular control. Now the question is that how to measure these harmonics, right? So practically, if you want to measure the harmonic, so you have to use either DSO, the digital signal oscilloscope. This is like digital signal oscilloscope picture, and you have to use power quality analyzer. Power quality analyzer for the 3-phase and for the single phase. The concept of the power quality analyzer is that this power quality analyzer will be like having codes, or you can say that the clamps, and these clamps will be like connected across the input side.
अभी टाइम भी मॉनिटर तो रखते हैं सर, पता चलेगा। देन सीपीयू के लिए अपन कह सकते हैं कि मेंटेनेंस के लिए गया है, मॉनिटर इज देयर।
Yes, and in SMPS you have power electronic devices, correct? So power electronic devices is there. So those power electronic devices will try to extract the non-sinusoidal current.
सर इसको बस 1 मिनट पकड़िए।
एक्चुअली पीसी जो आहे ना त्याचा मॉनिटर आहे ना
तो हाँ असं आहे का? इसे काम करें मत।
हाँ
वैसे भी आपका पीछे डेढ़ ही है ना, तो ये लीजिए, मैं आपको पीछे देता हूँ, वो नीचे पड़ा हुआ
ओ सर
You can say that okay, this particular equipment is like distorting the current in this way. So this will be the TSD, right? So these are the two major equipments whenever you are going for the laboratory experimentation and going for the industry part. So you will have to face these two equipments, right? These two equipments will be like utilized to study or to analyze the waveforms, because in power electronics, waveforms are very, very important. So you have to analyze the waveforms by using these devices. You can analyze the harmonics, you can analyze the TSD, you can analyze the shape of the waveform. I have captured results. These are the like results captured by the power quality analyzer. Why I am doing this? Because I just want to show you that your loads, or you can say that your daily usage loads that you are using at your home, how they are like responsible for degrading the quality of the power, right? So see this this is like second figure. This figure is like figure taken for the, or you can say that the power quality measure for the desktop computer, right? So when you measure the power quality for the desktop computer, you will find that the TSD in the source current will be like 44.7%. Next, see the laptop. When you measure the current across the laptop or measure through the power quality analyzer and go for the TSD analysis, you will find that TSD is like 35.9%. See, printer will be there, so TSD will be like 52.3%. When the tube light, you measure the current across the tube light, you will find 15.1%, right? When drilling machine will be there, so you will find 11.5. So everywhere you are finding that the TSD value is like greater than the 5%. That means these devices are like distorting the current waveform. Correct? So these are like few practical results. I just want to include and I just want to show you that how the daily loads, they are distorting the power quality. Correct? Now I just want to explain this next DC to DC converter, because second portion is like related to DC to DC converter. First I have gone through this rectifier. Now I just want to explain this DC to DC converter, because you will find that there are so many applications already there in this system related to the DC to DC converter. So these are the classifications of this DC to DC converter, right? You can classify this DC to DC converter. This DC to DC converter is like nothing but you just want to convert this fixed DC to this variable DC, or you can say that you just want to regulate the DC, right? This is the function of the DC to DC converter. Chopper that you have gone through in your power electronic course, this is like nothing but the extension of the chopper is like nothing but the DC to DC converter, because you have to use a combination of inductor and the capacitor, right? And you can define or you can develop different configuration for this DC to DC converters, correct? So in this DC to DC converters, classification is based on the switching operation, right? Whenever the hard switching is there, soft switching is there. So all these things are related to the research only, right? You can go through this, but definitely this classification will be like based on the research, right? So if you are like having interest in developing a new control or new topology for the DC to DC converter, definitely you can go through the different topologies available in the literature, and then you can define and you can design your own topology for the DC to DC converter. And the problem is like that in conventional DC to DC converter, switching will be like hard, you can say that efficiency will be like lower, and stress across the switches will be like there, more stress will be there across the switches. And another is like that if you want to increase or decrease the voltage level or voltage gain, that is like high gain converters. So they all are like coming under the category of this DC to DC converter. So if you are interested in the research portion, you can go through the DC to DC converter topologies, and then you can define your own topology, right? And you can design the hardware, small hardware for this DC to DC converter. I just want to explain the two DC to DC converter, that buck converter and the boost converter, because these two classical converters are frequently utilized in several applications. Like whenever you go for the applications related to the EV, applications related to the renewable energy, so you have to come across these two classical converters, right? So I just want to give you a like analysis of these two basic, you can say that the converters, DC to DC converter, and then I will move towards the application part. So purely I will be explaining about the solar photovoltaic system design part. So first go through this DC to DC converter part. If you want to analyze this DC to DC converter part, you just need to follow these two rules, two principles, that is the voltage second balance rule and ampere second balance rule, or you can say that the charge balance rule, right? So whenever there is a like inductor in a circuit, so this inductor in a circuit will be like that, it will not support an average DC voltage across it, right? That means the area under the inductor voltage curve in one single period will be like equal to 0. right? So this principle is always like utilized to analyze the DC to DC converter behavior. Similarly, the second one is the charge balance. Same will be there whenever you want to go for the area under the capacitor current curve, right? For one period, so that current should be equal to 0, right? So this way, these two principles are essential, and these two principles will decide the placement of the inductor and the capacitor, because you cannot place randomly inductor and the capacitor in the different DC to DC converter topology, right? First, you have to identify the position, that at which position you just want to place the inductor and the capacitor, so that volt second balance rule will be like applicable and the charge balance will be like applicable. So based on this, you have to define the converters, and based on these principles, there will be like three converters. That is the buck converter, or you can say that the step down converter, step down chopper. Another one is the boost converter, step up converter, right? And the third one is the buck boost, right? Step up and step down. So there will be like combination of buck and boost. Now the two important principles are there. One is like inductor. So always think like that, inductor will not allow the sudden change in the current. Suppose if inductor is connected in the circuit, say this is your inductor. If this inductor is connected in the circuit, so this is the current that is flowing through the inductor. So this will be the voltage that is developed across this inductor, and this inductor will always store the energy by virtue of the current that is flowing through it. That energy is like half Li square. Now, when you try to stop this current, this inductor will not allow that phenomena. Right? What will happen? This inductor will try to maintain the same direction of the current, even if you are like switching the mode. Whenever you are like switching from one mode to another mode in the operation, then you will find that this inductor will try to maintain the same direction of the current, because this inductor has already stored some energy in the form of half Li square, right? So this inductor will always try to release the energy through the same direction. So the current direction will be like same. When the current is coming, this is like charging. So when the discharging will be there, the current voltage direction will be like different, current direction will be same. So it will try to maintain the same direction. So you have to use this property of the inductor. And similarly, the property of the capacitor is like that. Capacitor stores the energy by virtue of the voltage that is developed across it, right, in the form of half CV square, right? So the capacitor will not allow the sudden change of the voltage, correct? Suppose this is the capacitor, and this is the current that is flowing, and this is the voltage that is developed across the capacitor, right? So when you are switching the mode, so this capacitor will not allow the change in the voltage like this. You can not go through like this, right? But this capacitor will try to reverse the direction of the current, right? But the voltage direction will be like same. It will try to maintain the same direction of the voltage, and current direction will be different. In inductor will try to maintain the same direction of the current. Voltage polarity will be like different whenever you are switching the mode, right? So these two properties will be like utilized to analyze the converter. So first converter is like buck converter, and this is the like figure for this buck converter. Buck converter means you have to use this switch, right? You have to use this second switch. This is your inductor and capacitor at the output, and this is your load. And this is the duty ratio. The duty ratio will be like V0 will be equal to D into V of S. So D value is always between 0 to 1, right? So whenever you select the value of the D between 0 to 1, you will find that V0 is always less than Vs. That means this is like step down chopper, right? Or step down
Excuse
converter.
me, sir.
That is why.
The slide is
Yes.
not visible.
Okay. Let me again share my
The slide on which you are writing, I think that is not visible.
Wait. Now it is visible, sir.
Yes, sir. Yes.
Okay. So I was explaining about this buck converter, right? And this V0 by Vs is equal to duty ratio, and this duty ratio will define the step down condition. Suppose you have like input 10 volt, and if your duty ratio is 0.5, so you will get at the output V0 is equal to 5 volt, right? You can calculate from this, correct? So this duty ratio is the ratio of the output by input, you can say that, for this buck converter only, right? Now you can go through the realization and go through the operation. So you just have to define the operation in two parts, right? One is the DTS operation. That means whenever the operation will be like for the turn on of the one switch. Here you will find that there are two switches. See, sorry. Here you will find that this is the like classical configuration of this buck converter, and switch S1 and S2 will be there, right? This is like S1 and S2. Whenever you are using this single pole double throw, then it is like only one switch, you can say that. But when two single pole single throw switches are utilized, that is switch S1 and S2 will be there. So if you are going operation of this buck converter, you will find that at one time your S1 will be on, so that period is known as DTS period, and at the second time this S1 will be off, so this S2 will be on. In this case, you will find this. So this is like 1 minus DTS period. So you have to analyze your converter for both the periods, for the DTS period and for 1 minus DTS period. This is like conduction period, you can say that. So see, for this DTS period, S1 is on and S2 is off. Carefully observe this, right? Because when one switch is on, so behavior will be like different. When another switch will be there, that will be like on, so then behavior will be different. So for the first switch, whenever you are going for S1 is equal to on and S2 will be off, so you just need to follow this. This is V in, this is the path, this is the path through the inductor and then through the capacitor and the load, you can say that. So this will be your conduction, correct? Now you can apply the KVL, you can define the voltage VI, so VI will be equal to this, the voltage across this capacitor VL, the voltage across this capacitor VC or V naught, you can say that, and you can also define the current, right? And whenever you are able to define the current value that is going through the inductor, right, you just need to define the slope, and accordingly you have to draw the waveform. So carefully observe this, right? So you just need to use this law and you have to define this current IL. This IL will be equal to 1 by L VL dt, right? And this VL is nothing but VI minus V naught. Why VI minus V naught? Whenever you are going for the KVL in this loop, for the first mode of operation, you will find that this is minus VI plus VL plus V naught will be equal to 0. So you can say that VL will be equal to VI minus V naught. Right? This is like KVL applied in the loop, and you will get VL value. This is VI minus V naught. And if you want to calculate IL, which is always equal to 1 by L VL integration dt. So you can apply this, you will find that this is the slope for this IL. So for this duration, current IL will be like linearly increasing. Why linearly increasing? Because this V naught is always lesser than VI, because you are operating for the buck converter. So this quantity is positive. This quantity is positive. That means the slope will be like rising only. So your current will be like rising from a lower value to higher value for this DTS operation, right? Similarly, you can also calculate the slope for the 1 minus DTS operation. So for that case, you have to observe this circuit, right? During this period, this switch is off, right? This switch is off means supply is like cut off from the circuit. So in this case, this capacitor has some energy, this inductor has some energy. So they will try to maintain the same direction of the current, right? Voltage across the capacitor will be same. Current across the inductor, that will also like same direction, and this will be the path. Now you can again apply the KVL, you can find the voltage. The voltage is like VL plus V naught will be equal to 0. So VL will be equal to V naught. Now if you calculate the IL value, the IL value will be equal to V naught by L integration dt, right? So in this case also you can calculate IL, in this case also you can calculate IL. What about this IC? This IC is always equal to IL minus I naught, and this I naught is a constant quantity because you have already assumed that the load is basically a DC load, and that load is taking constant current, correct? So you can also develop the waveform for IC. You can develop the, you have already developed for IL. You can also write down the equation for the voltage drop across S1 and S2. See, in this first case, voltage across S1 is what? 0, because S1 is on, so that is like short circuit. So the voltage across this S1 is 0, and what about this voltage across S2? During the first period, VI will be the voltage across this S2, right? The entire VI will be applicable across this. Same way you can calculate here. In the first case or in the second mode, switch S1 is off, so there will be a voltage that is VI will be equal to VS2, correct? So in this case, you can calculate the voltage across the switches. You can also calculate the current. Whenever this switch S2 is off, so the current through S2 is 0. Whenever the current S1 is on, the current through S1 is like same IL. So IL you have already calculated, same current will be like flowing through the switch S1. Similarly, you can also calculate the current that is flowing through S2, because already S1 is off. So when S1 is off, the current flowing through S1 is 0. S2 ke across current, the same IC current will be like flowing, IL, IC, same current will be like flowing through this S2. So now you have to draw the waveform, right? These are the important waveform that you need to draw, that is voltage across the inductor. Already I have calculated this. This is nothing but VL, current that is IL, load current I naught, current through the capacitor IC. Source side current is nothing but you can say that the IL current, same current will be there. current and voltage across the switches S1 and S2, right? So these are the important waveform that you have to develop, and already you have calculated the value IL. IL value will be equal to VI minus V naught. You have calculated this VI minus V naught divided by L dt, and for the second mode IL will be equal to V naught divided by minus V naught divided by L into dt, right? So that there will be like linearly increasing from this. For this particular mode, the first mode is like DTS mode, second mode 1 minus DTS mode. So for 1 minus DTS, it is like decreasing linearly, right? Because of this negative value, and again it is increasing and decreasing. So this will be the waveform for IL, and the average of this will be like I naught, right? Because you can say that IL is like going in two parts. One is like going through this load, and another one is going through this IC. So this IC is nothing but subtraction of this I naught from IL. So same way, just subtract this I naught, this is your I naught. So subtract this I naught from this IL value, you can draw the waveform for IC. Correct? Now you just want to draw the waveform for the current through the switch S1 and S2. So you have already gone through that when S1 is on, current flow through the S1. So current flow through the S2 will be 0. When S2 is on, S1 is off, so current flowing through the S1 is 0. Current flowing through S2 will be like this much only. Right? And same way you can also develop the waveform, draw the waveform for VS1 and VS2. Now, why I am drawing this waveform, I will tell you. Because after drawing this waveform, I just have to apply the voltage second balance rule and charge balance rule. You can say that by using those rules, I just want to calculate the value of the inductor and capacitor, because ultimately you have to design the inductor and the capacitor value for the buck converter. Correct? So the voltage balance rule will be like that. You just have to calculate the area under the curve of this voltage, right? So you just have to take this area, calculate the area for the entire duration. Entire duration means for DTS plus 1 minus DTS. This is the entire time period, which is equal to, you can say that the TS, right? For the TS time period, you have to calculate the area, equate equal to 0, and then you can say that you can find the value of the inductor, right? Same way, you can calculate the area under this current, or you can apply the charge balance rule, calculate the area under this IC curve, you can able to calculate the capacitor value. So these are the two important, you can say that the calculation. So for those, you have to draw the waveform for the buck converter and for the boost converter. So now I am calculating the value. First, you have to develop the relationship. That is like very simple, right? If you apply this volt second balance rule, already I told you, if you apply this balance rule, right, you just need to take the area for the entire duration, right? Entire duration means Vi minus V naught will be the voltage VL across the inductor for this DTS period, right? And this minus V naught will be the voltage across this inductor for 1 minus DTS period. So you just need to take the summation of all the voltages, equate it equal to 0. You will find this relation V naught is equal to D into Vi, and this D is nothing but the duty ratio, right? This D will decide, you can say that this D will decide that how the output will be there, how the output will be related to the input. Correct? And always the D value will be like varies between 0 to 1. Now, this is like realization. Realization means in the initial part, I just want to like analyze by using this S1 and S2 only. Now you have to realize that actually what kind of switches will be like applicable. So for S1, you just need to utilize the IGBT or MOSFET, because you have to control the S1. And S2 is like non-controllable. You can say that it will be like automatically controlled in the second mode only. So there is no need to go for the another IGBT, right? Here you can use this, like, but the cost will be higher, because the IGBT cost will be like higher than the diode cost, right? So it is better to advise like this, go for this S1 switch. This is like controlled switch. You have to provide the gate pulse at this switch, and this S2 will be like diode only. Power diode you can take, right? MUR based power diode you can take. Those power diodes will be like applicable for this second switch. Correct? So this is like realization, how the realization will be there. Now the important point is that how to calculate the inductor value and how to calculate the capacitor value. So for the inductor value, two things are there. Either you can apply during the DTS period, either you can apply during the 1 minus DTS period. What is the application? You have to calculate the slope, right? And based on that slope, you just need to calculate the value of the inductor. So this is like DIL by dt. You can take this, right? So there is like small change. DIL by dt means this is like delta IL. This is the ripple that is present in the inductor current, and these ripples are always controlled by the designer only. It is always in the hand of the designer that you want to insert how much ripple. Say you are interested in 10% ripple, so you can say that this delta IL will be decided by the designer. So delta IL by delta T, and which is equal to the slope, and slope during the first DTS period will be Vi minus V naught divided by L. You can observe these things from the waveform, clearly visible there, Vi minus V naught divided by L. And this is like, you can say that delta IL, and the time is like DTS, because you are observing for the first operation, that is DTS. Similarly, if you want to observe for the second operation, you can calculate this delta IL by 1 minus D into TS minus V naught divided by L. Now the question is that you can use any formula to calculate the value L, but I am using this second formula, right? Why? Because in the second formula there is no concept of this input voltage Vi, right? Only output voltage is there, right? So it is easier to calculate the L value from this formula only. That is why this second formula is preferable, right? So that L value will be like calculated based on output only. No need to consider the input, right? So L is equal to V naught into 1 minus D delta IL F of S. F of S is nothing but the switching frequency, and the switching frequency will decide the TS time, at how much time will be there, and this DTS and 1 minus DTS will be decided by the duty ratio. So everything will be in your hand. You can calculate L, you can calculate C, and you can play with the buck converter and the boost converter. Same concept will be applicable for the calculation of the value of the capacitor. You have to apply the charge balance rule, right? So charge balance means you just need to take the area under the inductor capacitor current, right? And area is like half base into height, and base is like TS by 2, because total time period is TS, so half time period is TS by 2. The current that is going is like delta IL by 2, because rest of the period is on the below the x-axis, you can say that, and delta IL by 2 is the above the x-axis. So you just want to calculate the area of this period. See, this was the waveform. This was the waveform for IC. So in this IC, this is nothing but your delta IL by 2, and this is your time period, that is TS by 2, right? TS by 2, because the entire time period is, this time period is like total time period is TS, and this is the time period, that is TS by 2. So half TS by 2 delta IL by 2, and which is equal to C into delta V naught, right? Charge is calculated C into V. So delta V naught is the ripples present in the output voltage, and this is again decided by the designer, that how much ripples are like applicable in the voltage. So based on this formula, you can calculate the value of this C, delta IL divided by 8 V naught F of S. F of S is the switching frequency, correct? Now the second converter is the boost converter, DC to DC boost converter, and in this converter you just have to think that your output voltage will be like greater than the input voltage. This is like step up converter, right? And this is the formula for this duty ratio. So based on this formula, output voltage will be like equal to Vs divided by 1 minus D. So let us say D is equal to 0.5. So when you take this D is equal to 0.5, V naught will be equal to twice of Vs, right? So there will be double the voltage, right? Now, can you analyze that what about this D is equal to 1? When you put the value D is equal to 1, what will happen? This V naught will be equal to Vs divided by infinite 0. So that V naught will be like infinite, but this is not true. Whenever you put the D value equal to 1, then what will happen? This switch will not operate, because that will be like second mode of the operation, and this load will be like discharging through this capacitor only, right? So immediately after few time or after few seconds, you can say that the entire load will discharge, or you can say that this entire capacitor energy will be discharged through this load only, right? So ultimately at D is equal to 1, you will get V naught is equal to 0. So always remember that you have to maintain the D value less than 1, right? The value of the D will be like varying between 0 to 1, but it should be less than 1, not equal to 1, correct? And practically, if you want to go for this boost converter, so the D value will be like, this D value will be like 0.6 to 0.7, 0.4 to 0.7. Practically, this boost converter will be like applicable, or will be like very suitable for this D value of 0.4 to 0.7, right? Not more than that and not less than that, because practically there are some drawbacks related to this conventional boost converter. So this range of the duty ratio will be like good enough to calculate the output voltage, to get the output voltage, or you can say that to step up the output voltage. So this is again same operation, you just need to apply. The only thing is that configuration is different. Here the inductor is like applied on the source side, then the switches are there, then the capacitor, right? Same you have to analyze for the DTS period and for the 1 minus DTS period. And I am again telling you why I am analyzing these two things, because for both the periods, you just want to draw the waveform for IL, IC, current through switch S1, current through switch S2, voltage across switch S1, voltage across switch S2. Everything will be like designed and developed, and then you can draw the waveform, and based on that you can use the ampere volt ampere second balance rule, you can say that, and then charge balance rule. Or you can say that you just need to take the area under the curve of the voltage VL and IC current. Then you can able to calculate the value of L and C. And our ultimate target is to calculate the precise value of the L and C. Another important thing is that while I am using this analysis, I have assumed few things. That means that non-idealities will be there. That means I have considered that these circuits are ideal circuits. Ideal means there will be no voltage drop across the switch S1, S2. But practically, if you are thinking of the switches, suppose if you are using diode, so there will be a voltage drop, forward voltage drop for the diode. Let us say Vf is equal to 0.7 or 0.8 volt. But I have considered that all the switches, all the devices, or all the passive components are like ideal only. Ideal means there will be no resistive component across the inductor, or you can say that in the inductor winding there will be no resistive component. You can think that there will be no ESR, right? Equalizing series resistance, equivalent series resistance for the capacitor. So there will be no ESR. So these ideal conditions will be considered for the steady state analysis, right? Then only you can say that you can carefully analyze these two circuits, that is buck converter and the boost converter, and then you can calculate the L value and the C value, correct? So same way you can go for the analysis for this DTS period. So in the DTS period S2 is on. When the S2 is on, this VI is connected through L and through S2, right? So this will be the path, correct? So in this path you can calculate VI, right? VI will be equal to what? VL, correct? And you can develop this IL value. You can calculate this IL also. Same way you can go for this second mode. This S2 is off and this S1 is on. So this inductor has some store energy in the first mode. And then in the second mode, it will try to maintain the same direction. And this inductor will try to release the energy through this path only, right? So in this case, half Li square will be like stored. And now this half Li square will be like going to this load, correct? So you can analyze both the things. Same for the first case, IL 1 by L VL, you can calculate this is the VIL by L, right? During the second mode, you can say that the current, the voltage will be here will be VI minus V naught, and here this VI minus V naught is negative. Why VI minus V naught is negative? Because this V naught is greater than VI, because you are talking about the boost converter, right? So that means you can say that this is negative. Negative means slope will be like decreasing. This is positive, slope will be increasing. So this kind of the waveform will be there for the current I, correct? So this is the waveform for IL. For the first DTS mode, this is VIL by L, right? For the second mode, VI minus V naught by L. Why this is decreasing? Because this VI is always less than V naught for this boost converter, correct? Similarly, you can draw the waveform for IC, right? In the first mode, the load current is like flowing through the IC, right? So the same load current will be there. So you just need to draw this IC will be equal to minus of I naught, right? Because for the first mode, IC will become equal to minus I naught. Carefully observe this from this waveform, that for this mode, this is the first mode. So this is the I naught that is flowing, and this is the direction of the IC. So you can observe this. This IC will be equal to nothing but I naught, correct? So you can develop this waveform for IC, and for the second mode, the same current will be there that is flowing through this IL. Only thing is that you have to shift your current below the I naught level, right? You just need to shift below I naught level, because this IC will be like having two components. IL will be like having two components, IC and I naught. The same case will be like there in the buck converter. So you can draw the waveform, and then you can calculate the value of the inductor and the capacitor. So inductor value is like calculated based on this. First you can define the duty ratio by just applying this rule. Then by taking the slope, you can calculate the value of the L, and then by taking the area under this curve, you can calculate the value of the C. So here you just need to calculate L, you just need to calculate the value of the C, and from this you can calculate the duty ratio relation. See, so if you are like applying input-output relationship, so this is the VI voltage for this DTS period, and this is the VI minus V naught voltage for this period. So from this you are able to calculate the V naught and VI relation. This is the relation that already I have given at the first slide of this boost converter. Now realization. Realization means same. This S1 is like not required to control, so you can use the diode in place of this S1, and S2 is like required to control, so you can use any control switch like IGBT and the MOSFET, correct? And again slope will be taken, right? Calculate the value of the L. right? Same way you have calculated for the buck converter. Same application will be here. Calculate the value of the capacitor. So I'm not going in detail of this. I just want to give you the overview of this buck converter and boost converter, so that now I can shift the base to the application part, that how this buck converter and the boost converter will be like utilized for different applications, right? So application of this DC to DC converter in the PV system, right? And this is the important application, you can say that, because whenever you are like operating with the PV, so think of that, suppose you are having 5 panels, 5 PV panels are there, and for one panel, the MPP voltage will be like 30 volts. So you will get total 150 volt, right? And if you want to connect this 150 with a 3-phase inverter, say this is the 3-phase inverter. So the 3-phase inverter AC side will be like 415 volt. According to the 415 volt, you will need 700 volt at the DC, right? So you just need to step up this 150 to 700 volt or 650 volt. Minimum 650 you will require at the DC side. So for that case, you need this extra stage. So this is the first functionality of this DC to DC converter, in order to step up the voltage that you are getting from the solar PV array to the desired level. That level is like maintained by the inverter, because inverter needs this much of the voltage level, so that it can convert the current, or you can say that, into the AC. In that AC can be like integrable to the existing grid. Second function is like that it will try to handle the MPPT. MPPT is like maximum power point tracking, right? Maximum power point tracking means in the PV array you will find that one PV curve will be there, right? So on that PV curve you have to operate at maximum, so that you can able to extract the maximum power from the PV array or from the solar photovoltaic system. So for that case you need to apply this algorithm, right? There are several algorithms available in the literature, so you can go for like conventional one, whatever, and observe and incremental conductance based algorithm. So those algorithms will be like applied, and these algorithms will be like handled by this DC to DC converter, right? And again you can say that this DC to DC converter will always also act as a isolation between this inverter and the PV array, right? What is the meaning of that? Suppose this PV array is there and this PV array is not working, like at the open loop condition or at the open stage condition. So VOCC will be like higher than the VMPP, right? So this VMPP is 150, so VOC will be like, you can say, 180 volt. So when this DC to DC converter is not there, so entire 180 volt will be like appearing across this grid or this inverter. So that will be like, you can say that the inverter switches rating will be like higher required, right? 15 to 20% high rating will be required. So in this application, this DC to DC converter is required. So this is the same application, like elaborated in a better way. So features like it will require to provide MPPT or to control the MPPT, to provide isolation, right? And in order to maintain the output level at the input of this inverter, right? This DC to DC converter is always helpful in order to step up the voltage, right? So output voltage of the DC to DC converter is always maintained by the inverter. That inverter is like connected with this DC to DC converter, or you can say that DC link, right? So this way, this DC to DC converter is the important device for the grid connected solar photovoltaic application. In UPS also, this is like another important thing. Whenever you are connecting the UPS for this, you can say that grid connected system or for the renewable energy systems. So this DC to DC converter not only maintain the MPPT, right? It will also try to like inject the energy that will be like utilized to store in this store in the battery bank. That battery bank is always connected at this level. This is like, you can say that the DC link level. There is like DC to DC stage and DC to AC stage. So in between these two stages, capacitor will be there, right? This capacitor is known as the DC link capacitor. So this capacitor is like playing an important role. So at this point you are getting DC, so you can connect the battery bank at this system. So by using this converter, you can also say that you can transfer the energy. If the extra energy will be available from the solar side, that will be like transferred to the battery. So in the battery storage, you can regulate the DC output voltage if battery is fully charged or not charged, right? So this way you can say that this DC to DC converter can also be utilized in UPS, right? To maintain the MPPT, to extract the maximum power from the solar photovoltaic, to provide the isolation, to provide or to maintain the voltage across the battery bank that you have connected at the DC link, right? Because you just want to charge the battery, right? So everything will be like based on this DC to DC converter. Then inverter topology is, or you can say that the inverter is also like important, but the role of the DC to DC converter is like important on the DC side. Then the inverter plays a role that to convert the energy that is coming from the solar to AC, usable AC, try to synchronize the energy to the existing grid. So that thing will be like taken care by the inverter. Now, there are so many power electronic devices, so many renewables are available in the existing, you can say that the system existing scenario. So for all these distributed resources, you just need to utilize the power electronic medium, right? So this is like the power electronic interface, how the different power electronic systems or power electronic interfaces will be required, right? You can take any example. I have already told you the wind energy conversion system will be there. So you need power electronic interface. If the PV system is there, you need power electronic converter, power electronic DC to DC converter, inverter, everything you will require, that is power electronic medium. Micro turbines, you need power electronic medium. Fuel cells, you need power electronic medium, right? Battery bank, you need power electronic medium. So everywhere, if you are like connecting the loads, suppose you are connecting the load that is related to the charging battery, related to the computer, so you need power electronic interface. So in entire system, you are observing that everywhere you are like associated with the power electronic interfaces, right? So see the importance of this power electronic. Everywhere on each and every side, you will find that power electronic devices are basically utilized. So now I will explain about the grid integration of the solar photovoltaic system. Little bit about the hardware development. This is like interesting. I am not going into the research part of this grid interface solar photovoltaic system. Instead of that, I just want to give you an overview that how the different converters, different auxiliary circuits, right? Different sensing circuit, gate driver circuit, regulated power supply, power circuit, how these circuits will be like designed and developed in the laboratory, right? So that you will have some idea and you can select your project based on these things that, okay, for your final year project, you can go for the power electronic related project. You can select the project based on the EV technology. You can select the project based on the DC to DC converter. You can select the project based on the renewables, solar photovoltaic system, right? So for those things, you just need to go through the small hardware development process, right? So I just want to give you an overview and idea about this system, that how these systems will be like developed, right? So I'm like more focused towards the grid interface solar photovoltaic system, and I want to give you the auxiliary circuits requirement and the design and development process of different auxiliary circuits. And this is like single stage system. Directly you can connect your solar photovoltaic system to the existing PV existing grid system. This is your AC grid on this side, and on this side you are having PV. So directly you can connect by just using this single stage, that is DC to AC, right? So you just need to design this inverter, correct? So in this case, both MPPT control and the inverter control, both will be handled by this controller only, or by this inverter only, right? And second topology will be like, you have this double stage topology. So in this case, again, there will be like a DC link capacitor, interfacing will be there. On the AC side, inverter is there, so you can control this and you can control this. MPPT will be like handled by this DC to DC converter, and the inverter control and grid synchronization, reference current generation, everything will be like controlled by this inverter, right? Now, if you want to design this grid connected solar photovoltaic system in the laboratory, so this is like entire circuit configuration, and focus on this configuration, you will find that how many circuits you have to design, correct? The first thing is that, suppose you have solar PV array, right? And this is your grid. So first you have to design the boost converter. So carefully observe that in order to design the boost converter, first you have to design the L value. I have already given the formula for the designing of the boost converter, that L, how to calculate the L value. So you have to calculate L value. Then you have to select the switch for the boost converter, correct? Then if you are like coming to the inverter part, you have to design or you have to select the rating of the switches, because you need 6 switches, right? 6 switches for the inverter. Carefully observe this. Then the DC link capacitor, because on the input side of the inverter, there is a DC link capacitor. You have to precisely calculate the value of the DC link capacitor and the voltage across the DC link. So these are the two important things: the voltage across DC link and the DC link capacitor, and the boost inductor, switch rating of this, both the inverter and the converter. Then on the output side, you just need to connect the interfacing inductor, right? These interfacing inductors are essential to transfer the power from the inverter to the existing grid at the point of common coupling. Because see, you can observe this, the power will like transfer from V1, V2 divided by X into sine of delta, right? So this X will be like necessary to transfer the power from one side to the other side, right? From inverter side to the point of common coupling side. So you have to design this LF, the interfacing inductors carefully. And another function is like that they just want to like mitigate the harmonics, source current harmonics. You can say that the harmonics that was developed because of the switching nature of this switches. So those harmonics will also be like suppressed by using this. So this entire thing is like power circuit, and this is your non-linear load. Non-linear load is like you can develop, you can use diode rectifier. So all these diodes are connected. So three-phase uncontrolled diode rectifier is there. You have already gone through your course. So in that case, you have studied this, that okay, whenever you are having uncontrolled diode, right, or diode is there, so that is like uncontrolled rectifier. Connect RL load across this. This is like non-linear load, and I have also given the impact of this rectifier on the input side. So whenever this rectifier is connected at the load side, so input current will be like this distorted nature. I think you have gone through this, right? I have already given this. This will be the input waveform because of this rectifier. So we just want to utilize this inverter for transferring the active power that is generated by the solar to the grid. And also this inverter will also help in mitigating this source current harmonic and also help in improving the power quality. Correct. So this entire scheme that I have mentioned is like development of the power network. Now you have to develop the auxiliary circuit. The first one is the sensing arrangement you need to develop, signal sensing by using the sensor, current sensor and voltage sensor. Then shifting circuit. Shifting circuit is like a special kind of the circuit, will be required only in few applications. Why? I will tell you. Because in few of the applications, whenever you are going for the microcontrollers or the DSP, so in the microcontroller and DSP, you will have unipolar ADC. Right, so the signal that you are giving at the ADC, that analog to digital conversion point of the microcontroller, right? Because on the microcontroller board you will have ADC ports, right? So when you give the signal to the ADC, so if the requirement of the ADC is like unipolar, so you have to convert the signal into unipolar. So this is the signal that is coming, you have to convert it to unipolar, and this is the gate driver circuit that you have to define, and deadband circuitry if required, and the complementary circuit means suppose you are getting 3 pulses and you want to generate another 3 pulses, so those will be like complementary pulses of the incoming pulses. So these are the 3-4 important circuits, and this is the design of the power network. So all these will be like covered during the next 4-5 slides. So first you have to design the power network. So from this network you have to calculate the boost inductor value. This is the boost inductor. Then calculate the C value, selection of the DC link voltage, selection of the DC link capacitor, and selection of the semiconductor switches and interfacing inductors. So boost inductor value will be decided by this formula. Here you have to decide the ripples. Ripples will be decided by the designer. This frequency will be decided by the designer. So you can take for the boost converter, you can take like 10 kilohertz, 15 kilohertz or 20 kilohertz practically, right? And for the inverters, you can take 2 kilohertz, 3 kilohertz or 5 kilohertz, right? This way you can select the frequency. Otherwise, if you are referring any paper, any reference paper, you can follow according to that paper. If you are referring any guideline, you can select according to that guideline, right? And if you are like using in the laboratory, so this is like thumb rule for the boost converter, you can select for 10, 15 kilohertz. Then how to calculate the DC link voltage? So this is the formula for the DC link voltage calculation. You have to use this formula to calculate the DC link voltage, right? And the actual phenomena of the DC link voltage is like that. Suppose this is the DC link voltage. Suppose this is 700 volt, right? So this voltage should be greater than the peak to peak voltage of the AC side voltage, right? So peak to peak voltage of the AC side is, this is like 339. This is again 339, and this peak to peak will be like 678. So always your DC link will be greater than this 678 volt, so that there will be a smooth transfer of the energy that is coming from the solar photovoltaic to the grid, right? So this is the calculation of this VDC. This is the important part. You have to carefully calculate this VDC. According to this reference value, your entire operation will be there. Whenever you are going for the closed loop operation, then carefully calculate this value. Then you have to decide the capacitor value. The capacitor is important, right? That capacitor is like a midpoint, or you can say that the interfacing between DC to DC converter and DC to AC inverter. So carefully calculate the value of the capacitor, correct? So by this formula, you can calculate this PTC is that you can say that the available power at the DC link, or you can say that the available power because of the solar photovoltaic array. This is the voltage. This is the ripples available in the DC. So suppose you just need to take 2% ripples if available in the DC. So based on that, calculate the value. Correct? Now, semiconductor switches. Important thing for the semiconductor switches, you have to select both voltage and the current rating. Right? this voltage rating is selected based on the DC link voltage plus extra 10% margin is given. So this VDC is the DC link voltage and this VD is the 10% of the VDC, so that you will get a safe margin of the voltage. And accordingly, you can also calculate the value of the current. So current will be like IR plus IP. IP is the peak value of the current, or IR is the ripples present in the current. So ripples is always like 5% of the IP. So first calculate IP, then take the 5% of the IP, and this is again the safety margin. 25% safety margin is the maximum you can take, right? And you can calculate the current value. Based on this current rating and the voltage rating, you have to select the switch, right? So that your switch will be like capable to handle this much of the voltage and this much of the current. Now you have to select the interfacing inductors. Interfacing inductors are also important, correct? Because the two functions will be there related to the interfacing inductor. First, they will try to like transfer the energy from the inverter output to the grid at the point of common coupling, and then second main function is like they are also utilized to suppress the harmonics, or you can say that the harmonics present in the output voltage, output current waveform because of the switching action of the inverter switches. So here, this is the formula FSW. You have to take the switching frequency of the inverter, right? Generally, this modulation index will be like selected between 0.95 to 1, right? Full utilization, you can say that. And this delta IL is again 5%. This is again depending on the designer, that how much ripples that you are allowed to the system, so that factor will be like decided by the usually designer only. So this way you can calculate all these things, and after calculating these things, you can select the switches. One important aspect is also there. If you want to go for the snubber, right, you can also design the snubber. I think already you have gone for the snubber circuit for the SCR. So the same snubber, or you can say that the same function of the snubber will be there. This is like you can say that the series snubber or the shunt snubber. So generally the shunt snubber will be there. Combination of R and C, you can say that will be like utilized to suppress the high amount of the voltage that will be like applicable across the switch, so that there will be like bypass through the capacitor, right? So that snubber is also important. So if you are like going for the laboratory development, or you can say that the prototype you want to develop in the laboratory, so you can also design the snubber circuit. So after designing these things, snubber, rating of the inductor and the rating of the switches, calculation of the inductor, calculation of the capacitor, calculation of the voltage across the capacitor. So you can develop the inverter and the power network. So this is the inverter that I have developed in the laboratory, right? So this is like you can say that 4 lag, 2 level inverter only, but lags are 4, right? So each and every lag will be like for one phase, and one is like if you are going for the 3-phase 4 wire, you can use 4 lag. Otherwise, if you are going for 3-phase 3 wire, directly use 3 lag, right? 1 lag will be like remaining there, no need to worry. And this is like, this one is your snubber, right? This is the resistor, this is the capacitor, right? And this is the diode, right? So this snubber is connected for each and every switch, right? And the switch is like, I have selected this IGBT, right? According to the requirement. And the gate pulse is provided through this port, the input port, you can say that. And here you are providing the AC, and here you are providing the DC, right? So this way you can say that you can design the inverter with the snubber circuit in the lab itself, and you can use this inverter. Either you can design single phase HVs, you can say that, and you can design 3-phase 3 lag, you can say that. So you can use this inverter for your application, and I just want to use this inverter for my application, and my application is like related to solar photovoltaic integration to the grid. That means the power that is coming from the solar photovoltaic need to be connected to the grid, need to be integrated to the grid. Now the important aspects are the auxiliary circuits, because see, I told you at the beginning that if you are like doing something related to the power electronics, you need have some knowledge of this sensing arrangement, you need have some knowledge of this control, so that you can control the controller, digital controller. So control algorithm will be required, and sensing arrangement will be required, right? So first of all, measuring of the voltage and current, you need voltage and current sensors, right? So LEM based sensors are particularly utilized for the laboratory development prototypes and for the industrial purpose. They are like nothing but current transformer and the potential transformer, right? So only thing is that you have to design these circuits accordingly as per the requirement, right? So suppose you want to design for the current sensing circuit. So for this current sensing circuit, suppose this is the input wire, right? Current is flowing, let us say 5 ampere current is coming from this way, right? And this is like the terminals, the transformer terminals. You can connect all these terminals so that the entire range will be like 25 ampere, because this is like LA25, and this will be the output, right? So this way current is coming and going through this transformer and like this way. Now one measuring port will be like given and two ports will be like there for the supply. Supply means plus 15 to minus 15. So I have already told you in the starting that how to generate the, how to design the regulated DC supply. So you can design the regulated DC supply, then you will get at the sensor terminals, right? And through the measuring port, you just need to select the R output, right? R I node. The selection of this R I node is important. So you have to calculate first I node current and then you have to calculate R I node. So this I node will be like responsible to capture the signal, or you can say that to extract the signal, that the current signal you can say that is going through this sensing arrangement, right? Current sensor. Everywhere you will find that the output of the current sensors will always be a voltage signal only, right? So for both the sensors, current sensors and the voltage sensors, the output will be like a voltage signal only, right? So you can get the output. Later I will explain about this amplification, no need to worry about this. So you just need to assume that okay, at the output you are getting output signal. Suppose input is 5 ampere, at the output you are getting 500 milliampere signal or 500 millivolt signal you will get. Because I told you now that for the current sensing and for both the voltage sensing and current sensing, the output will always be a voltage signal. Same you can apply these things for this voltage sensing circuit. You have to select one sensor, right? The two terminal will be like connected across the sensor. Two terminals will be there for the regulated DC supply, plus 15 to minus 15, and this is the RI node that you have to connect across the measuring terminal, and you have to calculate this value carefully. First calculate I node and then calculate this RV node, and then you can say that you are getting the output at this point, correct? But the output that you are getting after the sensing arrangement will be like sometimes distorted in nature and sometimes the amplitude will be lower. So two things will be like required. You have to amplify the output and you have to condition the output. So for that case you need amplification and conditioning circuit at the output of the sensor, right? So that the output will be like perfectly safe, perfectly sinusoidal and free from the ripples and with sufficient magnitude, because sufficient magnitude is required to inject that particular signal to the ADC of the controller, because that signal will be like going to the ADC of the controller. So that is why this signal amplification circuit will be designed. This is nothing but a very simple circuit. Just take the operational amplifier IC, right? This is nothing but the TL01 op-amp IC. This is like three level, you can say that three stage circuit. One stage is like for the scaling, that is for amplification. So one potentiometric arrangement will be there. You just need to move the knob of the potentiometer. You can shift the signal magnitude. And this is for the smoothing of the waveform. So you can observe this from the waveform. This is like the DSO waveforms. So you can say that the output will be like perfectly at 1 volt. Current, this is the voltage signal. These are the three current signals. And see, the current is like distorted. Why the current is distorted? Because I have considered the three-phase rectifier, uncontrolled rectifier at the output with R and L. And L value is sufficiently high. So because of that, the shape of the current will be like this only. So this shape will be like having TSD 28%. So your ultimate target is to reduce this TSD, and the second target is to inject the power that is coming from the solar photovoltaic to the grid. So for that function, I am trying to develop these auxiliary circuits. This is like how you design, and this is your amplification board. See, this is buffer, scaling, buffer, and for one phase, this is for second phase, this is for third phase, and this is your potentiometric arrangement. And this is the pictorial view of this current sensor and the voltage sensor. See, these are the three current sensors connected. Output of the sensors is going to the amplification circuit, and the output of the amplification circuit will be going to the shifting circuit, because whenever you are using microcontroller and the DSP, you just need to shift the signal to the unipolar level. So you just need to focus on this part only, that how these things will be designed, right? This is like designing on the dot PCB. You can also use your plain PCB, right? Plain PCB designing is also like more sophisticated, and you can say that more reliable, right? But there will be like requirement of the either PCB designing machine, or if suppose without PCB designing machine you want to design in your lab, that is also possible. You can use Express PCB software, and through the Express PCB software you just need to select the size of the PCB, then design your entire circuit on that software, then take the printout. This is like alternate way. I'm just telling because somewhere if you are not having the PCB designing machine, right, and you just want to design your circuit on the plain PCB only. See, the first alternative is like you can design your circuit on the dot PCB, right, and you can accordingly you can connect below the PCB and you can solder. But second option is like that you can design with plain PCB, right, without using the PCB machine. That is like First, you have to design the entire circuit on the Express PCB software. Then take the printout. Then you have to like put your like plain PCB on that printout only, right? Because in plain PCB you will have two sides. One side is like copper coated, one side is plain. So the copper coated side is like placed according to the size on that particular paper. That paper that you have taken the printout of that design, and then you have to like iron that particular PCB, cover the PCB with some paper and then iron that particular PCB for like half an hour. And after that, you just want to like insert that PCB in FeCl3 solution so that the portion that you have marked in the Express PCB software, so for that portion only the copper will be there, and for rest of the portion the copper will be like etched from the PCB, right? So that you can say that this way you can design the plain PCB without using the PCB machine. Correct. So this is like alternate way, and the best way is like you can go for the dotted PCB. That is also a best way. Then design of this power supply. Power supply is like very important because for each and every auxiliary circuit you need regulated DC power supply. Correct. So this circuit already I have given at the starting that 230 volt input will be there. This is the transformer. This transformer is nothing but step down transformer 230 by 15 0 15, and at the output there is rectifier and then capacitive arrangement. This capacitor you just need to utilize 35 volt at least, because peak to peak voltage will be like around 26 or 27 at the output of this transformer, so that this will be like in the safe margin. So 35 volt and 2200 microfarad you can select. These are the regulated IC, and this is like 25 volt 1000 microfarad. So this is like pictorial view. See, this is the input coming from the transformer, rectifier, bridge rectifier, input side capacitor, regulated IC, and output side capacitor and the output. You can design this in the lab itself. Then the bipolar to unipolar shifting. This circuit will not require for small projects, right? For the BTech project and for the UG project, right? So no need to worry about this. But directly, if you want to like shift the signal for some of the applications, you just need to this shifting circuit. And this is like arrangement of this two open biases back to back they are utilized, and two potentiometric arrangement will be like there. And by just moving the potentiometer, you can shift the signal like above the x-axis so that you will have a unipolar signal, right? This way you can design, and I have designed this in the laboratory itself. Then the deadband facility is important. Whenever you are like designing the inverter, so deadband is like very important. See, this is your first switch and this is your second switch, right? So you are applying a pulse to this first switch, right? So when the first switch is like on, second switch will be like off. So at this time the pulse is like coming down, that means the first switch is like going out of the service, and after this time you can say that the pulse will be there for the second switch, right? So there must be a gap between the incoming pulse, this is the incoming pulse, and this is the outgoing pulse, because if there is no gap, then for a brief moment both the switch will be like on, and when both the switch will be like on, there will be a dead short circuit across the supply that you have connected or across the input, right? That will destroy the switches. So in order to provide the switches, you have to provide a dead band between the incoming pulse and the outgoing pulse. So how it looks like? It looks like so. This is like dead band. You can say that 2 microsecond delay, 3 microsecond delay will be provided, and this will be like provided with the help of NOT gate IC, AND gate IC. 7408 is the AND gate IC, 14 pin AND gate IC. And in this AND gate IC, you will have like so many AND gates, and with the help of R and C combination. This R and C combination, by just varying the time constant, you can provide a delay, and this delay is helpful. That is why like it will try to save for the save across the sawtooth problem. You can say that, right? And provided in the inverter to avoid the sawtooth problem, right? So this is like nothing but the dead band circuit. You can say that. Then gate driver circuit. Gate driver circuit I have explained in the starting. So here I just want to explain the exact like requirement. On the input side, you have to calculate the R input based on the data sheet of this TLP250, right? And on the output side, based on the requirement of the pulse that you are getting and based on the requirement of the current, you have to select this R on and R off, right? And you can clearly observe that the pulse that input that are coming from the microcontroller is like 2.83 volt, and the output pulse will be like from -5 to +50, right? So this is the pulse, desired pulse. This is like generated up to this gate driver, and this pulse will be like given to the IGBT, right? So this is like arrangement, and this capacitor is like to provide the stability, a small capacitor to provide the stability across this pin 8 and 5. And this R on and R off will be like helpful in order to flow of the negative gate pulses, in order to stop the flow of the negative gate pulses, right? So this way you can design this gate driver in the lab itself, and you can provide the pulse to any of the power electronic switch. Suppose you are going for the project, and in the project you are having you just need to design this boost converter. So for the boost converter you have one switch, and across that switch you just need to provide the pulse. So for that case you have to design the gate driver, right? So carefully design the gate driver so that you can amplify the pulse up to a required level. These are the tutorial view of this different auxiliary circuits that I have developed in the laboratory, right? And you can also develop as per your requirement. If you are like going for the project, so definitely try to select the project from the power electronic domain, so that you can also develop these kind of small circuits for your project, you can say that. And I have already told you, you can select the project from the DC to DC converter side for EV charging, for high gain boost converter, right? For small projects also related to this grid connected solar photovoltaic system, you can develop small inverter. So these things will be like developed at the laboratory level. So you will get an idea about the actual behavior of actual operation and the problems associated with the hardware development, so that will be like helpful whenever you go into the industry. So this is the entire laboratory developed prototype for the complete grid connected solar photovoltaic system. And I have given an idea that how the different circuits will be like designed by using the auxiliary circuits, you can say that, by using the knowledge of the power electronics. So if you have any doubt related to this, you can ask me, right? So this is all about my presentation related to power electronic, concept of the power electronic, then some concept related to the rectifier, what is the problem associated with the rectifier, analysis of the rectifier, then DC to DC converter, and then some knowledge about the hardware development process.
रिसर्च कर सकते हो तुम।
एक्चुअली सर वही है, बच्चों को पावर इलेक्ट्रॉनिक्स का बेसिक ही नहीं पता, इसलिए वो
नहीं अपने को क्या AICTE के हिसाब से फंडामेंटल।
Now if you have like questions and your queries, kindly you
सर
can
इनसे
ask.
तो मेरे को थोड़ा गाइडेंस चाहिए। मेरे को ना ग्रिड कनेक्टेड इन्वर्टर बनाने का है, तो उसके लिए मेरे को एक आदमी चाहिए था। शायद ये मुझे दिख रहे हैं, हार्डवेयर वाले लग रहे हैं।
फुल लैब थी सर, बनाया हुआ बंदे ने। इनके लैब में जाने में एकदम
बढ़िया बंदा है ये, मेरे जैसा ही दिख रहा है मेरे को। ऐसे पूरा टेबल पे हार्डवेयर रखा था मेरा एमटेक का।
हाँ ये था ना इनके सब ग्रुप।
सर एक मिनट, अभी क्या बोल रही है?
क्वेश्चन है तो पूछो, डाउट है तो। हाँ सर पूछिए ना सर।
हेलो
Yes, sir.
स्टूडेंट्स, इज देयर एनी डाउट?
No, sir.
Sir, if you can just explain how we can integrate any converter with the grid, means what are the algorithm steps or something like that.
Okay. That I have included in the PPT. I can explain about that. For the integration of any converter, suppose if you want to integrate the inverter with the existing grid. So first and the foremost thing is that you have to extract some of the information of the grid. Suppose you have three-phase voltages of the grid. So you have to extract the information related to the angle and information related to the magnitude. So for that case, you have to use phase block loop, PLL, right? So the PLL will provide the information related to the source voltage or the grid voltage. Now, according to that information, you have to apply a algorithm, and that algorithm is like based on that which type of the controlling you want to control. Suppose you are going for the current control, right? So in the current control, you have to take the three currents and apply some ABC to DQ conversion, and like this, then you can convert those signals into the reference currents, right? So in this current generation algorithm, you have to generate three reference currents. Suppose I am talking about the three-phase system. So generate three reference currents, and these three reference currents are generated according to the PLL information, right? According to the PLL information means the output that your inverter will give always in the phase of the voltages of the point of common coupling. Correct. And then you can compare the reference current with the actual current. Actual current means the actual source current, so that there will be an error, and that error will always will be like mitigated and will be supplied for the pulse generation by using the hysteresis control and by using the PWM control. So let us go through that part.
And sir, what about the magnitude and phase angle with respect to grid? If you want
your-
to pump the
yes.
active power.
Sir, if you want to like inject the active power, so the magnitude of the active power will be like depending on the availability of the power at the DC link. Suppose you are integrating 1 kilowatt system and your system is like exposed to 500 irradiance, 500 watt per meter square. So the output power will be like 500 watt only, right? So in that case, that 500 entire 500 will be like available at point of common coupling, right? So you can control that. Suppose if you are using the droop control, right? So in that droop control, there are two components. One is ID component, another one is IQ component. This ID component is like utilized to control the active power, the injection of the active power, and this IQ component is like utilized to control the reactive power. In both the components, you have to define two reference. One is ID ref, another one is IQ ref. So whenever you go through the operation of this group control, or you can say that the decoupled control, that is the famous control utilized to control the grid connected solar photovoltaic system. So in that case, you will find that this ID ref and IQ ref, the reference values, you can say that in DQ frame, these will be like utilized to control active and reactive power. That is why we always mention that the active and reactive power transactions through the inverter will be like controlled by the control algorithm only, right? And suppose if you are using this kind of arrangement that is like visible on your screen. So in this arrangement, you are not controlling the active power, right? You are just controlling the entire active power that is coming. That power will be like shifted or will be like given to the grid, and you are controlling the harmonic component. That means you just want to mitigate the harmonics and you just want to supply the power. So both things will be there simultaneously, but control will be not there. This is like simple PQ theory, simple DQ theory. In the simple DQ theory, the direct conversion will be there from ABC to DQ, and then outer voltage loop will be there, that is like DC link voltage control loop. So output of the outer voltage control loop will be like current only. That current will be like combined with the D axis current, and then take the inverse. You will get three reference. These three reference will be like compared with the actual currents. Then you can generate the PWM pulses, right? Same thing is like shown here. See, from this, these are the three currents that you are getting, right? And this is the PLL. Any kind of PLL you can use. This PLL will provide the information regarding the amplitude and the angle. So from this PLL, I am generating this information related to the sine theta and cos theta. These information will be required for the conversion alpha beta to DQ. Again, DQ to alpha beta. Now, this ILD component is like only DC component having the DC part, and this is like reactive component. This DC component is like responsible for transferring the active power, but you are not controlling. Directly the available power is there at the DC link, that entire power will be like transferred to the grid, right? Now LPF is like, for further you can say that if still some of the distortions will be available, they can be like removed out. But the output of this DC component will be like combined with this PI controller output, and this PI controller output is like nothing but this is the outer voltage control. This outer voltage control loop is the slowest loop, but this is important. Why? Because this is like trying to maintain the actual DC link voltage with reference to the reference that you have created. The error will be generated, and this PI will be like given the output in the form of current. See, the property of the PI controller is like that. Whenever you are applying the error in the form of the DC, it will apply or it will provide an infinite gain, right? So that the error can be mitigated. And that output current will be like, the voltage will be like input, output will be current because of the proportional nature of this PI controller. And that output current is like, you can say that the input for the inner control loop. And this is like connected with this ID component, and then again take the inverse. You have three reference current. These three reference current will be compared with the original currents, and then you can apply the PWM. So in this case, active power is not controlled and reactive power is mitigated, because you have already inherently like IQ becomes equal to 0, or you have mentioned, or you have like forcefully kept IQ equal to 0. Correct? So in this case, controlling will be not there, but definitely you can transfer the entire active power, you can minimize the reactive power, and you can improve the power quality. But if you want to control, you can use droop control, having both the ID and IQ component will be there, and both component will be like compared with ID reference and IQ reference. This is the difference, and this is the way you can control, right, sir?
Yes, definitely, sir. Thank you for your answer. So, as there are no doubts from the students, actually, sir, I want to tell you that this is only 1 or 2 months they are in this field, because they are in
the
the
power
second year
field.
only.
Yes,
Yes, sir. They are in the
Yes, sir.
second year, so just started their journey in this electrical engineering field and even in power electronics. And
Right, sir,
I
right.
had just covered only powertronics devices till now.
Okay.
And only half wave rectifier. The analysis is
Okay.
going on.
So I think the initial 1 hour will be like interesting for the
Yeah.
initial 1 hour was the interesting, because during that part I have covered rectifier and the use of the
Yes,
power
sir.
electronic devices like that. Okay, okay.
Yeah, that was familiar to them, and even I think these things also, if they will hear again and again, then only they will come to know, okay,
Definitely,
at what
definitely.
extent the applications may go, and what is the complexity, what is the level of you can say hardware setup required. So
For the power electronics.
even
Correct,
they
sir.
get the feel of these things, even that is a great thing. So it was a, great lecture, sir, because you have started right from very fundamental topics, and then you have bring us to this level. So I think even in the institute like us, because we are running only BTech classes, BTech
Right, sir, right.
courses. So it is very hard to even see such kind of hardware setup and all of that.
Right, sir.
So I want to tell you that I also did my MTech in VNIT Nagpur. So
Okay, sir.
I also build a 5-level multi-level inverter.
Oh,
But
this is very nice,
I
sir.
didn't do that grid integration and all of that. I was in the drives part.
Right, sir, right.
So I hope the students will have idea and they will try to build similar things in their this student career.
Definitely, sir, definitely. My only advice to the students is that carefully go through the power electronic course. Still, you have like inverter and DC to DC converter. Sir will cover the part. And definitely after that, whenever you go for the project, for the final year project, try to select few projects from the power electronics, because power electronics is a very beautiful and very interesting subject. And you will have lot of applications related to the current industry scenario, right? If you want to go in the industry, right, so many industries are like looking for the power electronic engineers, right? Because right from the beginning of this renewable energy era, beginning of this electric vehicle era, lot of applications are like related to the power electronics. So each and every industry is like trying to search for the power electronic engineer. So if you have some basic idea of the hardware, definitely you will get good job at the end of your degree. So try to select the topics or select your project from this domain.
Yes, yeah, definitely, sir. And even in our electrical engineering field, this is the only field wherein you can bring something to physically, yeah, you can say in
Correct,
life,
sir.
and you can do something. Otherwise, everywhere just some analysis or maybe simulations, only those things, especially in power system domain. So it is like it's a tool, so we can apply it in any field also. So variety of applications are there. So thank you, sir. Thank you very much for your lecture. So I thank you from on behalf of our Phenolics Academy of Management and Technology, and I also
Thank you.
thank our HOD, Dr. Chowda sir. I know that he invited you to this lecture, and it was a great listening to you, sir.
Thank you, sir. Thank you.
Yeah, sir. Thank you, sir.
Can I leave now, sir?
Yes, sir. So
Thank you, sir.
thank you, sir. Students, the feedback form is shared to you. So please fill up the feedback form and then continue your activities for this day. Thank you. कॉल कीजिए. मैंने पानी नहीं पिया अब तक, बोतल लेके बैठा हूँ, 1.5 घंटा हो गया. ये सब एंड करता हूँ ना,